So just imagine this entire parking lot pretty much filled with one mirror for a giant telescope, a telescope that will be the biggest telescope on Earth.
Yeah, so it's a little bit of a fudge because it's not a symbol that actually gets used that much. It's a circle with a line through it. It's actually more of an engineering symbol than a physicist symbol.
Generally speaking, in astronomy, bigger is better when it comes to diameter. All a telescope is a big light bucket. We just sit out there with a mirror and collect photons as they come in from astronomical objects.
Well, let's take the story back to the beginning, and again, as with most things in astronomy, it goes back to Galileo. Galileo's first observations with a telescope, he was using a refracting telescope, so a telescope with lenses in it, and the lenses were a few inches across.
But basically with optical telescopes, we don't talk about lenses anymore, we talk about mirrors mostly.
And the nice thing about mirrors is you can make them a lot bigger than you can make lenses, so you can build bigger and bigger telescopes.
The first telescope that I ever had some involvement with was when I was a summer student in Victoria in Canada. And that was at the Dominion Astrophysical Observatory. And they have a lovely telescope there. And it's 1.8 meters in diameter. Now, at the time it was built, back in around 1918, I believe it was for a short period of time the largest telescope on Earth. It was temperamental. There actually was an official stick next to it with which you had to hit some of the equipment to make it work. And so then we graduate up into what we might think of as medium-sized telescopes. And these are telescopes that are maybe, the mirror is maybe 4 meters in diameter. So those include telescopes that I've been to include the Canada-France-Hawaii telescope in Hawaii. So another very nice summer experience working at that telescope. And something like the William Herschel telescope, which is a British telescope in La Palma. Again, a very nice holiday destination. You probably see a theme coming in here. We tend to build telescopes where the weather is good. Some of the life of an astronomer is fairly hard. So when you go to Hawaii, you may think of beaches and palm trees, but the telescopes in Hawaii are on top of the mountain Mauna Kea. They're at 14,000 feet. You're oxygen deprived. It looks like the surface of Mars. You're above the clouds. You're jet lagged and you're working at night. So yes, you do get to go to the beach at the end of your observing run. But that's probably after 5 or 6 nights of very, very, very hard work. Well, Hubble is kind of the anomaly here, because I said in most cases bigger is better, but the Hubble mirror is only 2.5 meters in diameter. So what's so special about the Hubble? Well, first of all, it's in space. So it's not sitting at the bottom of this really murky, moving atmosphere, but not only the size of the mirror matters, but the quality of the mirror. And the mirror on Hubble was ground to a precision that I don't think has been equaled. It was incredibly, incredibly precise. Of course, that's a whole other story because it was precise in the wrong way and had to be fixed thanks to an accident in the measuring. But it was accurate to, I think, 1/50th of a human hair. So with the Hubble, it might not be the biggest telescope on the block, but it's certainly got some of the sharpest eyesight. Yeah, so then the next class of telescopes are something around the 6 to 8 to 10 meter in diameter for their mirror. So I've used the Magellan telescope in Chile. So I visited there and stood underneath that mirror, which measures 6.5 meters in diameter, which is pretty big. But we also have lots of telescopes around the world that have 8-meter mirrors.
And that's kind of the limit if you want to build a single lens or a single mirror. You can build a mirror 8 meters across, but that's really pushing the technology because you've got to build a mirror 8 meters across, which is optically perfect so that it can actually focus the light. So it has to be figured to within a fraction of a wavelength of light, and it's 8 meters across. It's from an engineering point of view, it's really pushing the limits. For example, if you take a mirror like that, and then you point it in a different direction, which of course is one of the things you want to do with a telescope, the mirror sags. And so you actually need to have the whole thing actively controlled with little pressure pads behind to push it back into shape. So you've got all this sort of active stuff going on, holding it into shape. So even today, the biggest telescopes, which are sort of 10, 11, 12 meters in diameter, aren't single mirrors. We've gone to this system where you use a whole series of little segments. So you have lots of hexagonal segments that all kind of join together like a honeycomb.
We have the amusingly named VLT, which is the Very Large Telescope, which is actually 4 8-meter telescopes in Chile. The next telescopes, the really big ones, are going to be a lot bigger than that. So one of the first ones that was bandied about was the OWL, the overwhelmingly large telescope, and that was proposed to be 100 meters in diameter. So for various reasons, that's probably not going to come about. So we've downgraded slightly to, instead of the overwhelmingly large telescope, the extremely large telescope.
I'm afraid we sort of gave up giving things exciting names some time ago. It'll probably end up with a more interesting name when it actually gets built, but for the moment that's what it's known as.
And that's going to have a mirror that will be 42 meters in diameter.
So it's a whole series of more than 1,000 individual segments that are all going to be joined together to make a single mirror, effectively, that's 42 meters in diameter, which, as you might imagine, is going to collect an absolute shed load of light. So we're going to be able to see things which we stand no chance at all of seeing at the moment. We'll be able to see planets like the Earth orbiting around other nearby stars, and even be able to study the atmospheres of those planets to figure out whether there's life on them. We'll be able to see stars in other galaxies where at the moment we can just see kind of the fuzzy blur of light. We're going to be able to see galaxies on the other side of the universe on the kind of accuracy where currently we can only see nearby galaxies. So it's going to completely revolutionise astronomy.
42 metres.
42 meters.
Shall we try and get an idea how big that is?
Yeah, sure.
What are you going to do? What are you going to do?
So one easy measurement I have is the computer that goes on my bike. So we're going to go outside, and I'm going to get on my bike and see if we can measure approximately 42 meters somewhere in the parking lot.
And that's the sad thing, these poor photons of light, they've been travelling across the gulf of space for 10 billion years, hoping some astronomer's going to catch them, and they run splat into the roof of your house, and that's it, it's all over. So we'll catch some of them. I mean, even with a mirror 42 meters in diameter, we're still not going to catch very many of them, but it's a much bigger bucket than we've had in the past, so we're going to collect a lot more light than we ever have before.
Okay, so I've got my measuring instrument here, which is my bike, and I have a little wireless bike computer. So that just sits on here. So I'm going to reset that now, and we're going to try to see if we can figure out just how big 42 meters actually is.
Where are they going to put this bad boy?
It's an interesting question, because obviously there are kind of astronomical reasons as to why you might want to put it in particular places. For example, there's some things you can only see from the southern hemisphere, there's some things you can only see from the northern hemisphere. So that's one issue. You want to put it somewhere dark, because you don't want light pollution to mess up your images, but equally, actually, these things consume rather a large amount of power. So at their peak, they can use as much power as a small town. So you need somewhere where there's kind of the infrastructure, that you can get electricity to them, you have road access and all that kind of stuff. So you can't really pick somewhere that's absolutely in the middle of nowhere. And finally, there's politics. You've got to put it somewhere that's politically stable. You probably don't want to put it somewhere where there's going to be a revolution, someone's going to nationalise your telescope 10 minutes after you've built it. And even, if you're trying to get money out of someone, it's usually easier to get money if you say, and I'm going to build it in your country. So there's lots and lots of things, and I think it will be finalised for the EELT sometime later this year, but it's still open for discussion at the moment.
Okay, so this distance is 42 meters that I've just traveled, and that's going to be the diameter of the mirror of the extremely large telescope that's going to be built. So just imagine this entire parking lot pretty much filled with one mirror for a giant telescope, a telescope that will be the biggest telescope on Earth.